Hello, my name is Regula Meierhofer and I'm working at Sandec, the Department of Sanitation, Water and Solid Waste for Development. I'm leading you through this lecture with inputs from my colleague Rick Johnson from WHO and Marina Peter from the Fachhochschule Nordwestschweiz.
This lecture is about water treatment and safe storage in low-income countries. Learning objectives. During this lecture, you should learn about what kind of strategies are required to increase the consumption of safe drinking water in low-income countries. Also, I will present you water treatment technologies, what their strengths and limitations are, and how they can be applied in the context of low-income countries. You should learn how demand for safe drinking water can be increased and what kind of financial and business elements have to be considered for drinking water at the community scale, such for example as in water kiosks, and at the household scale, such as for example during household water treatment. The situation regarding drinking water access and the quality is critical still in many areas in low-income countries. About 780 million people do not have access to improved sources for drinking water, but many more people do not have any access to safe drinking water. This is because water from improved sources often is not safe for drinking. There are very large disparities between urban and rural areas and also between rich and poor households. The UN General Assembly recognized the human right to safe drinking water in July 2010. There are different criteria that are related with access to safe drinking water. The first criteria is availability. That means water has to be available in sufficient quantity and the continuity of the service has to be guaranteed. Then water has to be safe for health and it has to be aesthetically acceptable. That means it has to be free of a strange odor or it has to be clear. It should be free of turbidity. The time and the distance required to collect the water have to be adequate. And water has to be accessible also for young people, old people, and disabled people. Last but not least, the price of the water has to be affordable. Those goals are expressed in the Sustainable Development Goals 6.1. They claim that by the year 2030, everyone should achieve universal and equitable access to safe and affordable drinking water. This is measured by the indicator of the population, the proportion of the population using safely managed drinking water. And what means safely managed drinking water? This is drinking water from an improved source that is located on the premises, that means in a household compound. It should be available when needed and it should be free from fecal and priority chemical contamination. The accessibility of water, the distance to the water source, is very crucial because the larger the distance to the source, the less water is being collected by the person collected water. And this has an impact on hygiene because if less water is available, also less hygienic practices are being practiced, which again has an impact on health. Also, the distance to the water source has a strong impact on the health and on the workload of women, usually the ones responsible for collecting and carrying the water. Also, there are studies that have shown that the larger away the distance the source is, the higher the recontamination risk for the water that is being collected at the source. Diarrhea reduction is associated with an improved drinking water service. While for unimproved water, we cannot expect any reduction of diarrheal diseases, improved water shows that we can reduce diarrhea by about 11%. If improved water is available near the households, in household compounds, we can reduce diarrhea diseases by about 23%. If the water is treated at the household level and if there are safe storages practices around, considerable diarrhea reductions can be achieved up to 48%. If a well-managed piped water is delivered into the house, this has even a larger impact on health. Then diarrhea diseases can be reduced by about 75%. I will now present you a video about a water kiosk in Uganda.
More than 1 in 6 people worldwide lack adequate access to clean drinking water. This problem is especially acute in low and middle income countries like Uganda.
Currently in Uganda, about 30% of the urban population and 40% of the people in rural areas do not have access to an adequate source of drinking water. In eastern Uganda, there are many groundwater wells in the area, but their water has a high saline content and cannot be used for drinking water.
So people are not able to have access to more or less safe water from the ground. So what people do in these times, they just go down to the lake.
The majority of people in eastern Uganda get their drinking water from Lake Victoria, which is highly turbid and contaminated.
In the past 8 years, scientists at AVAC have developed an innovative technology for water treatment, the gravity-driven membrane filtration.
We started with the installation of GDM water kiosks in Uganda in 2014. Right now we have established 5 kiosks in Bulwande, Busime, Lugala, Bulundira and Bumeru.
The difference between lake water and kiosk water is absolutely immense. And basically the key technology, which is the membrane filtration, is removing particles and it's removing turbidity from the water. This immediately improves the aesthetic quality, so the visual quality of the water. More importantly, the membranes remove pathogens or microbial contaminants which is in the water. You can think here of protozoa, you can think here of pathogenic bacteria, think of worm eggs, anything like this. This is removed. What this does is immediately improves the safety and the hygienic quality of the water, and that gives you a good end water quality at the kiosk.
Each of the kiosks treats about 6,000 liters of water per day, and we serve the schools in those areas as well as the local community.
Before this water project came, there were many cases of diarrhea and cholera among other diseases in the communities. But now, the consumption of untreated water from the lake decreased in these locations from 73% to 41%. 59% of the households use the kiosk water. The incidence of diarrhea among adults has dropped from 19% at the project start to 6%. And among children under the age of 5, it has reduced from 34% to 14%. The incidences of diarrhea and cholera have been reduced. Enhancing access to safe water unlocks opportunities for people by reducing their workload and improving health. The establishment of the GDM water treatment systems at the shore of Lake Victoria is an example of how putting scientific innovation into practice can improve the lives of communities in great need.
As you have seen from the video, different elements are necessary that people have a continuous and reliable access to safe water and that they consume this water sustainably. First of all, it's the technology that needs to work. So this can be a water treatment technology at the community level or at the household level. Then there needs to be safe storage approaches. This is to assure that the water remains clean after collection at the kiosk water tap. Then for the kiosk to run sustainably, it's very important that the kiosk has a proper business management, that there is sufficient demand from the people around the kiosk for the treated water. This is dependent upon the price of the water delivered at the kiosk, or in the case of household water treatment, people will only buy the products if the price of the product is adequate. Also, of course, the product needs to be available in the local market. So this means that there must be existing supply chains. Also, if something gets damaged in the water kiosk, there needs to be supply chains for replacement parts. The behavior is very critical for a working, sustainable, safe water consumption. So people need to have demand for treated and safe water. There needs to be community training and education to create this demand. People need to know how to treat their water if they use household water treatment, or they need to know that they can get safe water at the water kiosk. And then consistent consumption of safe water is very important to assure proper health. Because even if only a little part of the water consumed is untreated, this will again have an impact on health and could cause diarrhea. So in this chapter, we are going to look at different technologies for drinking water treatment, either at the community level or at the household level. At very different levels, water treatments are possible. There are large-scale centralized systems, usually in urban centers or in peri-urban centers, where a large number of people are supplied by the water. Because risks are very high if there is some contamination in the water and a lot of people are being impacted, there are very high and stringent quality requirements for the water treated. So the systems being implemented in large-scale centralized systems are usually quite complex technically, and they require quite high cost for investment and operation. Also, because these systems are quite complex, the operation and maintenance procedures are also quite demanding. Usually the responsibility for large-scale systems are with the government or with private companies. Water treatment is also possible at the community level, more in a decentralized manner, and examples for such community-level water treatments are water treatment kiosks. Here, the systems are usually a bit less complex. Also, a lower number of people are being supplied with the water, and because the systems are less complex, operation and maintenance is easier, and also the costs for the installation of the technologies are lower. Usually these systems are operated by the community, and therefore there is quite a large challenge for establishing the capacity for the community to operate these systems technically. Usually these systems are financed through the sale of treated water, and there is need to create demand in the community for the water treated. Water treatment also is possible at the household level. And this is very often the case where people do not have access to water that is treated more centrally or at the decentralized level. Usually these are low-tech solutions that can be operated by low-educated households, and the responsibility for financing those solutions, I mean, they are being bought in the market, and the responsibility for operation and maintenance is with the households. Also here, it's very important to create demand for those products, and also it's very necessary to educate the households on how to use those products for household water treatment and to use them consistently. For all those technologies, treatment technologies and systems, there is a risk for a recontamination of the water after the treatment. So that it's necessary to install technologies for safe storage to reduce this recontamination risk. There are different methods for the microbiological treatment of water. There are physical methods. They consist of boiling, pasteurization, Then settling and filtration, as well as UV radiation. The chemical method focus on coagulation, flocculation and precipitation, adsorption, ion exchange, and chemical disinfection with germicidal agents, for example, chlorine. There are also biological methods, normally in biosand filters or in combination with membrane filters and a biofilm developing on the membranes. And here, biological processes are responsible for improving the water quality. As many water treatment technologies are being challenged by turbidity, it's important that turbidity is being removed before water disinfection technologies are being implemented. Why is turbidity challenging water treatments? Turbidity uses up chemical disinfectants dissolved in the water. It causes the premature clogging of filters. It blocks UV radiation and it stimulates bacterial growth. Different methods are being used to reduce turbidity in the water.
Coagulation is usually a pretreatment step. Its goal is to change the fine dispersed particles into larger agglomerates that can be removed by sedimentation or filtration or both. In coagulation process, a metal salts such as aluminium or iron salts are added to water containing dispersed, often negatively charged particles. Aluminium or ions destabilize the particles by neutralizing their charge. Water is being mixed rapidly and pH might need a correction. These destabilized particles form flocks which grow larger during slow mixing and finally settle down and can be easier filtered out. On this picture you see a mobile water treatment plant where coagulant is added in this tank. Another method of reducing particulate matter content is a rapid sand filtration. Water passes through the filter media, which is coarse or medium-sized sand, which is loaded over the more coarse gravel layer. During filtration, solids get trapped, settle or adsorb onto the sand material. After trapped material accumulated in the first layers, the filter requires backwashing, reverse flow of water to remove accumulated material. The filters are operated at linear velocity of 1 to 40 meters per hour, which is considerably higher than in slow sand filters, which we discuss later. For rather turbid waters, roughened filters can be used prior to rapid or slow sand filtration or disinfection. Differently sized coarse material is used in roughened filters. The size decreases in the direction of flow. There are different configurations of roughened filters: upflow, downflow, or horizontal flow. In an upflow filter you see here, water moves from down to top and the retained solids accumulate predominantly in the bottom of the filter. They can be flushed out by reversing the flow or simply draining the filter.
Filtration methods are not only available to remove turbidity from the water, but they are also available to remove microbiological or chemical contaminants from the water. One of the options is slow sand filtration, which we will be talking about in the next slides, as well as membrane filtration with different pore sizes, leading to different applications, as well as ceramic filtration, a method which is mainly used at the household level for household water treatment.
Slow sand filters are operated at a slow filtration rates of 0.1 to 0.3 meters per hour, compared to rapid sand filters, which are operated at 1 to 40 meters per hour. Slow filtration rates allow development of a biological activity within the filter. Thus, a slow sand filtration is a combination of different biological and physical processes, including mechanical trapping, adsorption or attachment, predation, and natural death, leading to the reduction of solids but also micro and macroorganisms. Slow sand filters are usually downflow filters and are operated by gravity. Each filter requires ripening period of few days to few weeks until removal rates stabilize. Mainly the top layer of the slow sand filter contains a diverse microbiological community and particles, and it is also called Schmutzdecke. In the Schmutzdecke, predominantly the inactivation of microorganisms occurs. During membrane filtration, water is driven by pressure difference between the feed water and filtrate through a filter with pores of a defined size range. Usually polymeric membranes or sometimes ceramic membranes are used. Microfiltration has pores in the size of bacteria or higher and removes them and particulate matter by size exclusion. Ultrafiltration membranes are more tight and remove also viruses, which in the size of 20 to 80 nanometer. Nanofiltration requires considerably higher pressure, as the pores are small, but it is capable of retaining micromolecules and larger ions. Small ions, such as salt ions, can be removed by reverse osmosis, requiring even higher pressure. For disinfection purposes, ultrafiltration membranes are most common as an effective barrier against pathogenic microorganisms, including viruses and particles. Different configurations of membranes are available. In drinking water supply, hollow fiber membranes are commonly used. They can be different diameters and different ways. The water usually goes through the membrane inside and passes on the other side out. They can be also bound together in a bundle to have a high surface area. Spiral wound elements look like this, and basically this is a flat sheet membrane which is rolled together in a spiral together with a spacer. Those are commonly used in desalination processes. In wastewater treatment in membrane bioreactors, flat sheet membranes are used. Membranes need to be frequently backwashed to remove larger particles, microorganisms, and all kinds of material accumulating on the surface of the membrane. The layer which is formed on the top of the membrane is called fouling layer. The drinking water filtration systems offer constant and reliable operation, which however requires high degree of automation, reliable power supply, and relatively high cost. There are also gravity-driven systems on the market and in development, more suitable for remote applications.
Slow sand filters have the following characteristics. They remove about 1 to 2 log of bacteria and protozoa, but they are also able to remove heavy metals and organic matter. Against viruses, however, they have a limited effectiveness. Advantages of the slow sand filter are, as I mentioned, its removal of organic matter. This is one of the very few water treatment technologies that has the characteristics of removing organic matter. Since it is a bioreactor and the organic matter is being reduced, there is a reduced risk of recontamination because bacteria have less food for growth. Biosand filters can be constructed with locally available materials, and they are very robust. Also, they do not need any chemicals or energy for their operation. Limitations are that the slow sand filter needs the biolayer to be effective. This biolayer is called Schmutzdecke, and it needs about 10 days to build up. Now, if a slow sand filter is drying out, the Schmutzdecke is being destroyed, and this means that the filter is not effective anymore. So slow sand filters cannot be operated at very high turbidities because then the filters need to be cleaned frequently and the biolayer is being destroyed frequently. Therefore, if water is highly turbid, slow sand filters are not an effective solution for water treatment. Slow sand filters, they can be applied at the household level, or they can also be installed in centralized treatments. Characteristics of membrane filtration, mainly in traditional system, is the microbiological performance depends upon the pore size of the membranes, as previously explained. The advantages are that they are highly efficient in removing pathogens, and a lot of water can be treated at once. Also, membrane filters are able to reduce the turbidity of water. But same as with slow sand filters, if water has a very high turbidity, the filters are very quickly clogged. Therefore, turbid water has to be pre-treated. Limitations are fouling of membranes. That means that the membranes have been regularly backflushed and they have been disinfected chemically. So these are complex systems and they usually are very costly and they have to be imported in areas of low-income countries. Also, supply chains are required for replacement part. And in the case of reverse osmosis system, it's difficult to discharge the brine. For all those treatment technologies, recontamination during storage is a risk. Different characteristics apply to membrane filtration systems that are operated as gravity-driven systems. Here we have systems with micro or ultrafiltration, and here the efficiency depends upon the pore size of the membrane. Gravity-driven membrane systems are very simple to use. They also work with turbid water, and here they are an exception. We have operated such systems with water turbidities of more than 100 NTU in household systems, as well as in community kiosks, and we did not encounter any blockage of the systems. Also, gravity-driven systems, they do not require any chemicals or energy for the operation, because these systems allow the formation of a biofilm on the membranes, and because less pressure is used to operate those systems, the biofilm remains porous and does not clog the system. Limitations are that some of the systems that are being installed as gravity-driven systems, they do require backflushing, such as for example the Sky Juice system. And also here the membranes must be imported, and therefore it can be difficult to establish supply chains. These systems are less costly than the traditionally operated system, which require additional pressure and energy for the pumps. And here we do not require any pumps. But also these systems are subjective to recontamination risks during the storage. Gravity-driven systems can be applied at the household level or at community scale, but also in centralized systems. There are different products available for membrane filtration at the household level. On one side, we have the LifeStraw Personal. It's a product that has been developed by the company Westergaard Franzen, and coming from the first product, which was a straw halm to suck water from a pump, but which required a lot of pressure to sucking through the water, a water bottle has been developed, which uses hollow fiber membranes with a pore size of 100 nanometers, thus it's microfiltration, and the product costs about $25 to $40 per piece. Sawyer water filters have developed a filter which uses ultrafiltration with a pore size of 20 nanometers. It's a siphon filter which uses the hydrostatic pressure. Also, this system has to be backflushed and it costs about $50 per piece. Martin membranes, they have developed a gravity system for household application, which does not require any backflushing. Here, flat sheet membranes are used with a pore size of also 20 nanometers. And special for this system is that it doesn't have to be backflushed. One of these filters also costs about $60 per piece. An important filtration method for application in low-income countries is ceramic filtration. Ceramic filtration is mainly used to produce products for use at the household level. Ceramic filters can be produced locally in those countries. In ceramic filtration, water is filtered through porous ceramic material, and the effectiveness of the filters depends on the quality of the filters, on the firing process, and on the pressing of the ceramic material in the factories. That leads to the size of the pores in the glaze. Most of these filters, they are effective at removing protozoa and bacteria, but they do not remove any viruses. Sometimes ceramic filters are also impregnated with bacteriostatic silver. And if silver is applied in the production process for those filters, the removal efficiency can be increased. Generally, the removal rate of ceramic filters is about 3 to 4 log for protozoa and bacteria. The flow rate in ceramic filters is about 1 to 2 liters per hour. Ceramic filters are also sensitive to turbid water. They do treat turbidity, but if very turbid water is used for ceramic filters, these filters have to be cleaned frequently, and the cleaning process can lead to contamination of the filters and therewith destroy the effectiveness of the filter, because bacteria that are being inserted into the filter are not being removed anymore and lead to recontamination of the treated water. Attractive in ceramic filters is that they can be produced for a low cost price locally in low income areas, and they can be sold for about $10 to $30 per piece. And this is a price that also can be afforded by communities living in those areas. Also, the filters are very attractive as household water treatment products because the application is quite easy and people like to use filters to treat their water. Now I would like to introduce you to an example of marketing ceramic filters in Cambodia. This is the Tunsai ceramic filter, which has been developed by the organization Hydrologic Social Enterprise. And as you can see from the picture here, we have two types of filters: the normal filter, the Tunsai filter, and then an improved model, the Super Tunsai filter, with a better design that has some filter stands that enables to better withdraw the water, put the glass below it. And the Tunsai costs $12 and the Super Tunsai costs $22 US. Now, these filters have been marketed by two different approaches: direct sales and sales through microfinance groups. In the microfinance groups, women had the opportunity to obtain loans, and these loans facilitated the performance of the sales model. So the result of this marketing experiment was that direct sales led to about 16% of households purchasing filters, whereas in the microfinance groups, about 43% of the members purchased a filter. So we can see that microfinancing is an element that can increase the purchase of household water treatment products because it leads to availability of more money in the households, but also social norms can play a role here because the decision was made in a group and there might have been some group pressure on different women that it is important to treat the water at the house and a good idea to purchase such a filter. Also, very interesting finding of this experiment was that the Super Tunsai was sold 17 times as frequently as the Tunsai, although it was almost double the price. And this shows us that design is very important also if we work in the context of a low-income country. Also, people with a lower income, they have a preference for a better design and they like aspirational products. So another method for household water treatment is boiling. Boiling is the method which is most broadly applied in low-income countries, especially in Asia. It is a very old method. It has been recommended by the health workers since centuries. And of course, boiling is never applied at the centralized scale and only at the household scale. So the problem with boiling is that it uses a lot of energy. And there have been some calculations that said that the household cost could increase by about 10% only for the cost of boiling the water if additional fuel need to be used. Also, a problem is if the boiled water is not stored properly, because if it's stored in unclean containers, of course, the boiled water can be recontaminated again. One of the big advantages of boiling is that it disinfects almost all pathogens. Only very, very few spores, like for example, anthrax spores, are resistant to boiling. So boiling is one of the few methods that can be used to disinfect all the pathogens. Now, a question is, how long should water be boiled for the water to be safe? And here we come to pasteurization, because actually water does not have to be boiled at all to disinfect the water. We can use the pasteurization effect and heating up the water to 70 degrees Celsius for a few minutes has quasi the same effect as boiling. And this table gives you an indication of the temperature sensitivity of different pathogens. So if we summarize the characterization of boiling and pasteurization is we have a high efficiency against different classes of pathogens, and it's a very common technology which can be combined with cooking or with tea boiling. Also, one of the big advantages of boiling is that it's one of the few technologies that can be used to treat turbid water. Limitations are the possibility for recontamination, the very high cost for fuel, indoor air pollution, and also boiling can be quite time-consuming. Regarding the application, boiling is only applied at the household level. UVC radiation has been used for a long time for water disinfection. UVC irradiation is another method for drinking water treatment. The germicidal activity of UVC radiation in the wavelength between 200 and 320 nanometers has been used for water disinfection since the early 20th century. UVC radiation is also very effective in disinfecting the water. Bacteria, Cryptosporidium and Giardia are being disinfected at doses between 1 to 10 millijoule per square centimeters, whereas viruses and bacterial spores need a bit higher in irradiation intensity of about 30 to 150 millijoules per square centimeters. Different lamps are being used for UVC disinfection. Commonly used in the past were mercury UV lamps, which irradiate in the intensity between 50 and 150 millijoules per square centimeter. But very emergingly being used are also LEDs, which emit light in the wavelength of UVC. These UVC LEDs have the benefits that they are more environmentally friendly and they use less energy for operation. Still, they are more expensive than low-pressure mercury UV lamps, but there is a potential for them in future. UVC radiation disinfects bacteria by damaging their DNA. So the problem if too low doses of UVC radiation are being received is that bacteria and other microbes are able to repair the UVC-induced damage in their DNA, and they could restore their infectivity again. So to summarize UV irradiation, it is effective against all classes of pathogens, bacteria, protozoa, and viruses. It is very simple to use, and it is a very fast treatment that does not change any taste in the water. Limitations are that highly turbid water needs pre-treatment, and also the method cannot be applied without electricity. Also, for this technology, there is a need for a supply chain for replacement parts, which sometimes is difficult to establish in low-income contexts. The method can be applied either at the household level. You see here in the picture below is an example of the SteriPan, which is a relatively expensive product for trackers. But the method can also be applied at community scale and is currently in use in water kiosks, which are quite frequently installed in India. So the household product SteriPan, which is currently available in the market, costs about $80. And this is, of course, too expensive for application in a developing country contexts. But there are a lot of efforts currently going on for product development for cheaper products in this sector. Another method that uses irradiation, this time solar irradiation, is solar disinfection. Solar disinfection uses the full bandwidth of the solar light to disinfect the pathogens. So this is mainly UVA, but also parts of UVB. The method works by filling contaminated water into transparent plastic bottles and exposing them for 6 hours to the sunlight. More than 6 hours are required. If the weather is cloudy, then the bottles need to be exposed for about 2 consecutive days. During the sunlight exposure, the sunlight destroys the bacteria and the viruses. Viruses inactivation is about 1 log, while bacteria inactivation is about 3 log. A solar irradiation intensity of about 500 watts per square meter is required during 5 hours during a sunny day. But if the water temperature increases above a temperature of above 50 degrees Celsius, there is a synergy of UVA radiation and the temperature, and only about 1 hour of solar exposure is required for the water to be safe for consumption. Summarizing advantages and limitations, we have a microbiological performance to inactivate bacteria for about 3 log, and a limited effectiveness against protozoa and viruses. Protozoa are very easily disinfected if the water temperature increases above 50 degrees Celsius, and the inactivation of viruses is about 90%. The advantages of this method is that it uses locally very low-cost materials, such as the sunlight and locally available PET bottles. The method is very low-cost, and it doesn't change the taste in the water. Also, if the treated water is stored in bottles, the recontamination of the water is very unlikely. Limitations are that highly turbid water needs a pre-treatment. Then the method is highly dependent upon the weather. In area where you have a lot of fog or very frequent rains, the method is just not suitable. Also, the long treatment time, so you have to expose the water to the sun for some hours, up to 2 days, and only limited volumes of water can be treated. Also, a limitation is that quite a large supply of clean, intact, and properly sized bottles are being used. And this is a challenge because not everywhere in low-income areas such a large amount of reused bottles are available. Of course, this method is also only applicable at the household.
When chlorine is dissolved in water, it forms equilibrium between the chlorine, hypochlorous acid, and hypochloric acid. When chlorine is added to water, it reacts first with reduced compounds and is being destructed. At a higher dose, it reacts also with organic matter and nitrogen species to form chlororganic and chloramine compounds. If you look on this figure, we can see that at first the chlorine residual will increase, proportionally to the amount of chlorine added, until the mole ratio of ammonia to chlorine is about 1. Beyond that, addition of chlorine reduces total chlorine residual due to oxidation of some chloramine species. Breakpoint is a point at which complete oxidation of all chloramine species occurred. The location of this point depends on the presence of organic matter, nitrogen, and reduced inorganic ions. After the breakpoint is reached, free chlorine residual proportionally increases with a chlorine dose. The part of chlorine which participates in disinfection and is called chlorine demand. Chlorine residual is a chlorine which remains in water after the disinfection process, has been predominantly completed and acts as a safeguard against additional microbial contamination that could be introduced in water or in distribution network at the point of use. Recommended residual chlorine concentration is about 0.5 mg per liter of free chlorine, which should be applied to water during at least 30 minutes. Chlorine dose is being expressed in concentration multiplied by contact time, called CT value. CT99 means the concentration and time required to kill 99% of target microorganisms. In case of bacteria, the CT values are low, indicating the inactivation of bacteria occurs relatively fast and at low concentration. The time and concentration are considerably higher to inactivate viruses and very high for protozoa. Cryptosporidium oocysts are resistant to chlorine, which often does not provide sufficient level of inactivation to protect from a disease. Presence of particulate matter in water leading to high turbidity of water compromise chlorination, and water has to be clarified before it can be disinfected with chlorine. There are different forms of chlorine available, and it can even be produced on site by electrolysis of salt and water. The choice of the most appropriate form of chlorine will depend on such factors as scale and water volume which needs to be treated, skills available, safety management practices, and power supply reliability. Ozone is highly effective oxidant, not only disinfecting water, but also reducing color, micropollutant content, and other organic contamination. It is, however, expensive and doesn't provide residual protection. Due to high cost and relatively complexity, it is usually not used in an emergency context.
Summarizing on chlorine disinfection. With chlorine, we can remove about 2 log of bacteria and also viruses, but the method is not so effective against protozoa and cysts, especially against Cryptosporidium. This can be a problem if we have a project or if we work in an area where there are living people with a compromised immune system, or also if we treat water for small children. There we have to assure that also the protozoa are being removed by the method that we are using. The biggest advantage of chlorine disinfection is that it provides a residual protection against recontamination. The method is quite simple to use and local production is possible. Also, there are household applications which are being provided at very low cost. Chlorine does not work well if the water is turbid because organic material dissolved in the water reacts with free chlorine. Therefore, turbid water needs to be pre-treated. Also, chlorination changes the taste of the water, and this could lead to rejection among the community that receives chlorinated water. Also, dosage depends upon the raw water quality, and therefore it's not always easy to determine the appropriate dosage for water. There is a contact time required for the chemicals to react, which is 30 minutes. Chlorination is being applied at the household level, but also in centralized water treatment plants at the community scale as well as at the centralized scale. I would like to present you an example of the application of chlorine in a low-income country context. The chlorine dispenser has been developed by the organization Innovations for Poverty Action. The chlorine dispenser is a bucket containing liquid chlorine, which is installed near the source of water, where people collect their water in jerry cans. The chlorine dispenser has a valve that doses the required amount of chlorine for a 20-liter bucket. When people collect their water at the source, they usually pay for the water, and a very little amount for the added cost of chlorine is added to that water price. And an evaluation has shown that about 50 to 61% of the people use the chlorine dispenser regularly, compared to 6 to 14% in a control group that did use chlorine at the household level, but not taking the chlorine from a chlorine dispenser attached to the source. Also, the evaluation showed that the chlorine dispensers were still used after 2 years. Other products for chlorination at the household level are the safe water system, which contains liquid chlorine, which is produced locally, and a container for safe storage. This product is marketed at very low price and makes the chlorine available for household water treatment. Another product for household water treatment using chlorine are aqua taps, and they use sodium dichloroisocyanurate. The advantage of aqua taps is that they have a longer shelf life than liquid chlorine of about 5 years. Therefore, the product is often applied in emergency contexts. Another method for producing chlorine locally is water. Water uses electrolysis to produce a 6 gram per liter chlorine solution. So to produce this chlorine, a saturated brine solution is used and together with electrolysis. This method is applied in schools and health centers where larger amounts of chlorine have to be produced to treat the drinking water. Comparing the different water treatment methods for household water treatment or water treatment at the community level reveals us that the choice for the water treatment we want to apply depends on local criteria such as the local water quality at the source, cultural preferences, or also financial possibilities of the local community. Important selection criteria for products are their effectiveness, the durability, because it's always a challenge to convince people to invest for replacement parts, because this leads to an increase of cost, and the cost of the product. Then another point is an attractive design. It should be very easy to operate and maintain, and also the design affordability needs to correspond with cultural acceptability. If we would like to remove microbiological and chemical contamination complete, as well as turbidity, a combination of different systems might be necessary. So, in addition to water treatment technology, we have a challenge that water might get recontaminated if it is collected at the tap or at the source. Therefore, interventions to assure safe storage are very important.
Safe storage of drinking water can help to minimize such contamination risks during collection and transport, when the source is outside the home, as well as during household storage. Especially when water is treated at the household level, it's very important to store it properly so that the gains in quality are not lost. There are a number of characteristics we would like to see in an ideal household storage container. Perhaps the most important one is that the container should be covered and that there should be an opening which is small enough to discourage people from putting their hands into the container during water collection or from using a scoop or ladle to retrieve stored water. The opening, however, should be large enough to allow easy filling at the point of collection, and usually openings are between 5 and 8 centimeters in diameter, and ideally they have a screw cap of some kind. Although you don't want it to be too easy to insert hands into the container, it is good if the container can be cleaned periodically. And in some designs, a lid can be removed and the insides can be cleaned manually. Where this isn't possible, users are recommended to periodically add sand or pebbles and shake them about to clean the insides. You can also add soap or chlorine after removing the pebbles to wash the insides of the container. Water can be safely retrieved by pouring, but this requires some physical effort to lift the bucket and a risk of spilling. So it's preferred to have a tap which can be used to withdraw water. Taps should have a fairly large bore so that the flow rates are high. However, taps do break or leak, so they should also be simple enough to be repaired or replaced with local hardware. Often, storage containers are also used for transporting water from the point of collection to the household, so the container shouldn't be too large. Even a 20 or 25-liter jerry can is very heavy when it's full. And of course, a container should be strong and stable so it isn't easily tipped over or broken, and it's better to be opaque to prevent the growth of algae. If chemical disinfection is being used, it's good to use a container size that corresponds to an easy chemical dose, typically 10 or 20 liters. And finally, the container should be affordable and ideally available through local markets. Here are some examples of containers that were designed specifically for safe storage. This is the container developed by the U.S. Centers for Disease Control and the Pan American Health Organization as part of the Safe Water System. It's a modified jerry can that holds 20 liters of water and costs about $5. The Oxfam bucket has a lid with an opening and cap built in, and the cap is attached so you can't lose it. You can also completely remove the lid, which allows very efficient transport since the buckets can be stacked inside each other. These also cost around $4 or $5, and while they were designed at Oxfam in the UK, they're now produced all around the world. In many countries in Africa, 20-liter jerry cans are widely used for collecting, transporting, and storing water. They're fairly easy to carry on the head, though they are heavy, and have a small opening which prevents putting hands inside. Water is normally poured out of the opening. They're not easy to clean, and they can be quite dirty, like this example here from the Central African Republic. On the right, you see a modified jerry can being distributed in the Philippines after Typhoon Haiyan by the NGO Plan International with support from DFID. These jerry cans have a large screw top for filling that also allows cleaning. And they come with a built-in tap, that small red knob at the bottom. It's very easy to convert a standard plastic storage bucket into a safe storage container by drilling a hole through the plastic wall to install a tap.
Now we have learned about technologies to treat drinking water. But the technology is only part of an element of a strategy to assure that people sustainably consume safe drinking water. Another element are finances. So if we look at our case of the water kiosk, the finances we have now covered technologies for drinking water treatment. Technology is but only one element of sustainable safe water consumption. To assure that people in low-income country contexts consistently and sustainably use safe drinking water, other elements are important. One of them is finances. If we look at those water kiosks that have been presented earlier, the question is, have they a proper business management? What is the demand for drinking water? What is the price for water? Also, if we look at household water treatment products, the price of those products play a very crucial role for their application and their use. Also, supply chains of products are very critical. Going back at the business management of water kiosks, the ownership model can play a very important role for the functioning or not functioning of such a kiosk. A kiosk could be managed by a community committee comprising of different people, but the question is, can such an ownership model work well? Sometimes there are disputes or disagreements between different members of the groups. So a community kiosk is not only the only option for running of such a kiosk. There could be a franchise model, or it also would be possible to run such a kiosk as a private enterprise. Looking at such a kiosk, we need to think about financing of investment costs And there has been quite some research looking at income generation and cost of such kiosks. And very rarely such a kiosk is able to recover financing investments because the revenues that are being generated by such a kiosk are extremely low. But the kiosks may be able to generate sufficient revenues to finance operation and maintenance. A very crucial element to generate sufficient income is demand. How many people are there actually coming to the kiosk to buy the treated water? It is a very important element of income. How can people be convinced to come to the kiosks? So there needs to be PR, there needs to be public relation activities, and there needs to be community training and education to increase demand. If we look at demand, of course, the price of water plays a very crucial role. Is the price sufficient to cover operation and maintenance costs? Or is the price too high for the community to pay? It is not easy to define such a price. Then, if not enough revenue can be generated from the sale of water, we might want to think about additional potential revenue sources. In some water kiosks, the kiosk also sell energy. People bring mobile phones that can be charged, or in some of the kiosks also sell additional health products that could generate an additional income, because only if the kiosk is able to generate an income that enables the long-term financement of operation and maintenance, this kiosk can be operated sustainably in the long term as well. If the kiosk wants to operate sustainably in the long term, it's also very necessary to establish the capacity of the people operating the kiosks. So the people need to know how to do proper business management and to do it reliably, and also without having and letting disappear money that comes in. Also, people need to be able to manage the technical aspects of the kiosks. They need to be able to repair if there are any damages. They need to be able to clean the membranes or being able to replace some valves if they break down. So if we look at business model approaches of water kiosks, we have the different ownership models. Then we have different key activities looking at the value proposition. That means activities that generate an income. We need to look at customer relations and marketing, and that looks into community training, behavior change to increase demand, then the branding of the kiosk. We need to look at how many customers does such a kiosk have, and the number of customers is influenced by the population density. We have to look at competition. Are there other water sources around where people are maybe able to go to a river and collect water for free, which is not safe, but doesn't cost anything? We have to look at the behavior factors. Then we have to look at key resources in the model. That means what kind of technology is being used, what are the management requirements, what are operation and maintenance capacities and capabilities. Then we need to look at the cost structure. What are the capex? How can this investment be generated? Are there any donors around that are willing to invest into a kiosk without expecting to have the investment back? What are the operation expenditures, salaries? What are costs for maintenance? What are costs for electricity, for example, to operate pumps? And what is the revenue structure for such a kiosk? So product sale is one of the income sources, but we also could think about other potential income sources, such as donor support or government support. And the advantage of having a community managed system is that there is ownership within the community for such a kiosk. And we have seen quite some cases where actually the community is willing to support and pay repairs in the kiosk if something breaks down. The price of water at the household water kiosk, or the price for household water treatment products, is very crucial. And why is that so? About 4 million people in the world live at the bottom of the economic pyramid. Those people have an income of less than $1,500 per year. Among those, the poorest of the poor, 1 billion people, they earn less than $1 per day. Looking at this, price has a very crucial impact on the uptake of a behavior or a treatment method. If we look at experiments that were conducted by Poverty Action Lab to assess the price's effect on the use of health products, for example, deworming tablets in Kenya, bed nets, or water disinfectant or soap, we see that a small fee causes a very, very big reduction in the take-up of those health products. If we look at such high impacts of price or increases, we have to think of potential subsidies for health products, which could be carried by the government in the interest of a public health effect. So, looking at affordability, what does this mean for households? Affordability is one of the criteria for access to safe drinking water as defined by the Sustainable Development Goals. And an independent human rights expert defined optimal affordability as overall water costs of less than 3% of the household budget. Intermediate affordability is at 5% and minimal affordability is at 7% of the household budget. What does this mean for payment schemes regarding household water treatment products? We have the option of direct purchase of such products from shops. This is being applied in the case of cheap products and particularly fast-moving goods, such as, for example, chlorine liquid drops. But there are also options for paying products in installments if it concerns higher-priced products, such as, for example, filters. For filters also, we have seen from the example in Cambodia that filters can be purchased through microcredit. Also, we have to think about the option of a subsidy for a health product. However, the option of subsidy only works if we have a scheme options that provides a long-term subsidy, because the application of subsidies can be dangerous. If a product gets damaged and replacement parts have to be purchased, or if the product has to be replaced, it's not very likely that households are going to buy a new product for a full price if a subsidy is not available anymore. So what are the lessons that have been learned during promotion of household water treatment? Experiences with projects have shown that safe water has a very low priority and people are not very willing to invest a lot of money for it. So that means that products for household water treatments, they are not able to cost much. And people are only interested in low-cost products. But this again means that it is very difficult to establish viable businesses for entrepreneurs because they only can realize very, very small profit margins, and it's very difficult for those businesses to survive. Also, it's actually very difficult to supply such products into the remote areas where poorest people live and where people have often the worst water quality. Because of lacking infrastructure and bad roads, it's very difficult to establish supply chains, it's difficult to deliver products and to create access to replacement parts. It is very important to create demand and establish consistent water treatment, because only if people have the demand for safe water and continuously and consistently treat their water, we can realize health benefits. Such trainings require behavior change, and long-term interventions are required to establish behavior change processes and especially to consistently and strongly establish these new habits. So we have looked at the elements of technology and the element of finances to establish sustainable safe water consumption. And I have pointed out that behavior change and behavior change interventions are very important to increase demand for such products and also to establish consistent consumption of safe water. Such behavior change is important and consistent consumption is important to realize the health benefits.